Hi there. Welcome back to part 7 of my video lecture series introducing the standard template library. I'm Stefan T. Lowitt, and today we're going to talk more about algorithms, in particular the insert iterators and the sorting and related functions. So when we left off at the end of part 6, I had mentioned that when you are calling copy in order to copy a source sequence into an output iterator, you need to make sure that there's enough space in the output sequence to store all of the elements that are copying to it. So you can't do something like copy into an empty vector's begin because that will attempt to write off the end of the empty vector. But I mentioned that you could use something called back inserter in order to automatically add elements as you write to them. So I wanted to show you an example of what that looks like because that's a very important thing to know. So here I've got a vector that I'm going to be adding things to through copy to back inserter. So I start off with an array. This array has a few elements here, and this will be my source sequence. Then I've got a vector, and the vector is going to start off containing a couple other elements, 11 and 77. So I'm going to print out all the elements. I'm going to show you several ways to do this. So here's a handwritten iterator loop where I print out each element followed by a space, and then print a new line. And then I'm going to copy to back inserter. So that's what this call is. I'm going to copy from the array's begin to the array's end. Here I'm using a built-in array, so to find its end I need to use the size of trick that you've hopefully seen if you've been programming C or C++ for a while. And then I'm going to write to back inserter of V. So this little call is doing something interesting. V here contains a couple elements to begin with. It contains 11 and 77. And if I say back inserter V, what this gives me is an iterator. It's an insert iterator. This back inserter is a function, a template function, that's returning stood insert iterator. And what this thing is, suppose that I call this iterator I. When an STL algorithm, in this case copy, is writing to this insert iterator, it's going to be repeatedly dereferencing it, writing an element, and then incrementing it. So it could write deref I++ equals some element, in this case the element from the source. So what the insert iterator does is it's maintaining a pointer to, so if I've got this insert iterator I, it contains essentially a pointer. This is, internal implementation specific, but somehow it knows how to communicate with the original vector. And whenever you dereference the iterator and increment it, and then write an element to it, some STL machinery is saying, okay, I'm going to, instead of trying to directly write to an element, push back a new element. So every time I say this, it's going to be expanding the sequence through an ordinary call to pushback, and we know how that works. And it's going to be pushing back. In this case, the first element is a 22. And then the next thing I write is a 99. And so this is safe because we know that pushback will automatically expand a vector in linear time. Everything is good. Whereas if I simply directly tried to write to the end of the vector, then I would scribble off the end of memory, and I've got a bug, in fact, a security bug. That would be very bad. So this will flexibly expand the sequence, and then I could print out the container again. In this case, I'm going to use a for each algorithm. So for each element in vBegin, vEnd, use a lambda function to print out each element n separated by a space and then print a new line. So if I execute this, then I would expect to see the vector initially contains 11 followed by 77, and then after the copy of the back inserter, it will contain 11, 77 followed by 22, 99, 33, 44, 55, and we'll see what that prints. Now, I started off the vector containing a couple elements because if I simply want to construct a vector from a range, I should not use copy to back inserter. I could, but it would be gratuitously inefficient. I should just directly construct the vector from a range. This is something that everyone seems to run into. So even though I may have mentioned it in an earlier part, if I am constructing my vector, this could be just some arbitrary t, v, I could just range construct it from a first iterator and a last iterator. And that will make v a copy of that source sequence of elements, whatever first points to, whatever last points to. It's more efficient because it's not repeatedly calling pushback. The vector can be properly sized ahead of time, no reallocation, assuming your iterators are random access, everything is good. But in this case, I wanted to demonstrate a place where you really do need to use copy to back inserter. I could have written this any number of other ways. I could have, for example, resized the vector to actually add a bunch of elements all at once and then overwrite them. But copy to back inserter, I wanted to show that off. So then I wanted to demonstrate the sorting and related algorithms. So I can sort my vector. We've seen how this works. That's just a sort vbegin vend. And again, I can print out everything. I wanted to show you a third way to print out the elements in a sequence. This one is somewhat confusing, and in fact, I don't recommend it anymore now that we have C++OX and things like Lambda functions. But if you're working with code that used the old C++9803 STL, you may run into this also in examples. This is copy to ostream iterator. So this is a call to copy that's actually going to be doing printing. This says copy from vbegin to vend and write to this confusing thing called an ostream iterator. It's templated on element type, in this case int, and it's going to be writing to cout separated by spaces. So what an ostream iterator does is, this is something coming from the iterator header. Please include all of the headers that you need. If I have an ostream iterator, okay, suppose this ostream iterator is called I, and I constructed it telling it, okay, you're going to be fed ints, you're going to print to cout or any other stream, and then here's your delimiter space. Whenever the STL writes something like dref I++ equals lm, what this is going to be translated into is this iterator is going to be informed, okay, I'm writing an element to you, and instead of actually putting that into a sequence or calling pushback or whatever, it's going to send that to cout. So it's going to execute cout left shift lm, and then it's going to also print out the delimiter. This could be one or two calls, or it could be a single expression or multiple, and that is far too many left shifts. And in this case, my delimiter was space. This has simply been stored. That's what the ostream iterator is doing. This is useful if you need to get a STL algorithm that wants to talk to iterators to instead write something to a stream. But because you could simply do a for each with a lambda or other things with C++OX, copy to ostream iterator is not especially useful anymore. But if you see it, that's what it means. Then I'm going to do a binary search. So the STL, if we look at the working paper, it has 4 algorithms for binary search. This is sort of the first thing that people new to the STL will run into. There is an algorithm called std binary search. It is not what you want. What it returns, and it can be useful, although I've never personally found a use for it, it returns bool. So if you give it a first, a last, and a value, or a customized comparator, it's going to return whether this element exists in the sequence or not, according to a binary search. So, it's efficient. It's doing a logarithmic binary search, but it's only returning presence or absence. Not terribly useful. I mean, if you need it, then use it. But often when you're doing a binary search, you actually want the position where that element lives in the sequence. Std binary search will not give you that. Instead, you need std lower bound. This is what people usually think of as a binary search because, yes, it can be used to determine presence or absence, but more importantly, it will return the position in the sequence where the element exists. So it exists in 2 forms, taking a value and also comparator. We'll see what the comparator does. Right now, I'm just searching for a value. So if I go back to my program, I'm going to ask for the lower bound. This is that binary search algorithm in my vector v, and I want to find element 50. And then I'm going to print out the index of that iterator. So given this iterator, this here I'm just using auto, that's a vector int iterator. If I subtract vbegin, that's going to give me the index in the sequence, 0-based of course, where I found the element. Because if I just printed out dref I, that would show me what it points to, but not its location within the sequence. And then if I execute this, let's see what this returns. My vector started off with 11 and 77. Then I did that copy to back inserter, tacked on that array. And then I sorted it, so I get it in sorted order. And then I searched for 50 within the sequence. And what this returned is index 4. So there's a lot going on here. Let's look at what this is doing. Oh, I almost forgot to mention. Copy to back inserter could also be written more efficiently as inserted end. There are some times where you actually do want to write copy to back inserter, But range insertion is more efficient. So I could have written v insert at v end first last. This would be array and then array plus size of, the number of elements last. Here we go. And what this says is, okay, you've got a vector, it contains some elements, in this case 11 and 77, and I want to insert, add some parens here, 11, 77, end. So STL insertion always inserts before the iterator that you give it, so this is the end iterator. If I'm inserting before the end, that's right here. Very convenient to remember. And I'm going to be tacking on this whole range at once to my vector with whatever elements that I'm filling it. So they're equivalent in meaning, copy to back inserter and insert at end. But the difference is that copy to back inserter is going to call pushback, pushback, pushback on my vector. That's a lot of pushback calls. It's constantly testing the vector's capacity against its size. It's performing reallocation if necessary. What insert at end does is it's being told all at once, hey, I'm going to insert this source into the destination. So the STL is capable, and in fact does, figure out how many elements are in the source, resize the vector once, and then inserts all those elements. So it can be faster by a constant factor of like 2 maybe, then copy to back inserter. So if you want to insert at end, please do that. If you have to do copy to back inserter, okay, but do be aware of range insertion when that is an option. So I did lower bound, and it returned indexed 4. So there's a programming challenge that you may have seen on the internet that asks programmers to write a binary search. And it's actually deceptively hard. Something like only 10% of programmers can get it right on the first try without any bugs. I've taken the challenge myself, but it's somewhat unfair because I maintain the STL, so I know how a binary search works. Fortunately, you don't have to write a binary search yourself if you're using the STL. You get to use lower bound. And in fact, the difficulty that most people have when they write a binary search by themselves is they don't know quite what conventions to use when the element is not found. The STL uses a certain set of conventions, and if you ask me, they are by far the most useful conventions possible. So imagine that I've got my sequence, and I've sorted it, so I'm just going to use my favorite elements, 22, 33, 44, 55. So as you hopefully know, binary searches, like a lower bound, rely on the sequence being sorted. If the sequence is not sorted, according to the comparison, in this case less than, then using a binary search is not valid. So it's a precondition of the algorithm that the sequence be sorted, so you can always just call sort vbegin vend if you're not sure. So suppose that I call lower bound vbegin vend on this vector, and I ask for element 33. So it'll repeatedly look at the middle, see if the element is less than or greater than, and then subdivide. We don't know how a binary search works. And if I'm asking for 33, it's going to return an iterator to that element. Great, I found the element. Now, what happens if I have multiple such elements that I'm looking for? So suppose my vector was 11, 22, 33, 33, 33, and then 44, and then 55. Again, lower bound is going to return the first element in this subrange of equal elements. Okay, that's often what we want. What if the element does not exist like this? So suppose that I had 11, 22, 33, 44, and 55, and I search for 30. What does lower bound do? So the actual element 30 does not exist in the sequence, but what lower bound is going to do is it's going to return you the first position in the sequence where a 30 could be inserted and maintain the sort. So could I put 30 between the 11 and 22? I could not, because that would break the sorting. 11, 30, oh, down to 22, that's not sorted. The first position in this sequence where I could insert the 30 would be between the 22 and the 33. So if my sequence looked like 11, 22, 30, 33, 44, 55, perfectly sorted, everyone's happy. So because the STL always says, okay, I'm going to insert before an iterator, the first position in the sequence where 30 could be inserted is the 33. So if I call lower bound with 30, I would get an iterator to the 33. And then if I actually tried to insert 30 there, it would be inserted right before the 33 and maintaining the sorted order. So that's what lower bound does if it can't find the element, but there's a position to insert. Now, what if my sequence instead had elements that were too small? So if I had 11, 22, 33, 44, 55, and I ask, okay, what's the first position where I could insert a 99? Well, all of these elements are smaller than 99, so what the STL will return is the end. Because we've seen STL inserts before an iterator, so if I took a 99 and inserted it before the end, well, that would tack it on to the end of the sequence, because it would be inserting right here. And the sequence 11, 22, 33, 44, 55, 99 is perfectly sorted. Vice versa, if I ask for an element that's lower than all of the elements in my sequence, suppose that I'm going to search for 0, then it's going to return the beginning of the sequence, because if I insert before the begin, then that would tack on a 0 to the very beginning of the sequence. I would get 0, 11, 22, 33, 44, 55, preserving the sorted order. So no matter the result, the STL always has a way to express the location of whatever element you're asking for. Many programmers, when they're asked to write a binary search by themselves, they're not quite sure how to handle, what do I do if the element doesn't exist? They'll try to return like a invalid index, because they're typically working with indices instead of iterators, like -1 or so forth. Not quite useful and very difficult to get right. People get it wrong all the time. Whereas the STL, because it's using this begin end convention, can deal with cases like, okay, what happens if the element is less than everything, greater than everything, in between but doesn't exist? What if there are multiple copies, and so forth? So we saw briefly in the working paper that there was another algorithm called upper bound. So if I've got 11, 20, I can't spell or write, 22, 33, and suppose I want some copies, 33, 33, 44, 55. And I ask for the lower bound, we've seen that that returns, and suppose I'm asking for the lower bound of 33, then that is going to return an iterator here. I could also ask for upper bound, and that is going to return the last position in the sequence where I could possibly insert my value and still maintain the sorted order. So if it's ever confusing, just remember what would happen if I inserted this element. So the upper bound of 33 is here. It points to the 44. That's because if I insert before it, if I inserted a 33 here, it would maintain the sorted order. 33, 33, 33, 33, 44. Everything is good. So you should never expect that lower bound and upper bound will return you an iterator pointing to a copy of this element, because, as we've seen, if it doesn't exist, lower bound could return an iterator to an element that your number could be inserted right before. It could return end, and so forth. And same with upper bound. Even if it does exist, upper bound will return one past the last occurrence. But the returned iterator is very useful. Now, what if you want both of them? What if you want to find all of the 33s in a sequence, and you want to do so with a binary search that's efficient? You could, of course, call lower bound and upper bound independently. That would be two logarithmic binary searches. But there is an STL algorithm that will do both of them for you more efficiently, and that's called equal range. So if I ask for equal range, what that will do is return both the lower bound and the upper bound simultaneously. And if we look at what that's doing, that's actually returning something exceedingly useful. If I get an iterator here and view that as an STL range, remember the STL uses one past the end. So the range that this represents actually is the range of all of the 33s in my sequence. And this is the past the end value. So with an equal range and something like a vector where the iterators are random access, I can determine in logarithmic time how many 33s are in my sequence. Because I call equal range, subtract the iterators, constant time, and it says, oh, there's 3 33s in the sequence. Whereas if I try to do something like a count if, because countif works on unsorted sequences, it would inspect every single element order n. So that's why equal range is useful. And like I mentioned, it returns a pair of iterators because the type is obnoxious to mention. Using auto is very useful. Here we can see equal range takes first and last, and then returns a pair of iterators. So I can use lower bound and upper bound to ask, okay, is this element in the sequence? But I could just call it binary underscore search if I wanted just a bool yes or no. So that's why when I executed my program, it returned 4, because I was searching for the value 50. 50 did not exist in my sequence, but the first place where it could be inserted was right before this 55. So I'm going to get an iterator to the 55, and that's at index 0, 1, 2, 3, 4, and that's what it returned. So that's what lower bound is. So now you know the mysteries of the STL lower bound and why it's not actually called binary search. Now we've seen briefly that sort and lower bound and upper bound and all these other sorted operation algorithms take these function objects, functors, called compare or comparators. What that does is it allows you to customize the sorting of a sequence. So if I have if I use operator less than to sort a sequence, I'm going to get 11, 22, 33, 44, 55. If I use operator greater than, I'll get the reverse. 55, 44, 33, 22, 11. Of course, if I have equal elements, I would get, 55, 44, 44, 33, 22, 11. But what this means is that different elements will be ordered according to my comparator. So 55 is greater than 44, 44 is greater than 33, and so forth, and same with less than. So the STL by default always uses less than for comparators, but you can customize it and say, okay, I'm going to use greater. The helper that I believe we've briefly seen before is stood greater. That comes from the functional header. So greater is a struct, and because I've got the working paper open, we can actually look at that. That is in the clause 20, where is it? General utilities and function objects and comparisons. Here we go. So greater here, actually I can zoom in a bit. Greater is a template struct. So you can ignore the fact that it's a base class. In fact, that's not really useful anymore in C++OX. But it's templated on an element type, and its function call operator takes 2 elements by const reference and returns whether the first element is greater than the second. So this is a very, very thin helper. The reason why we need stood greater and stood less and these others is because these operators for things like built-in types, they're not real functions. So I can't literally say operator less than for int in my source code. I can't get a pointer to that function because it's just a built-in construct in the core language. That's why I need this helper class that will compile away to nothing because it's got the simplest possible body in its function call operator. And there's stood less and stood less equal and so forth. So the other extremely important thing is the STL's convention is to use less than like operators. So there's a mathematical term for this, a strict weak ordering. You can look it up on Wikipedia if you want, or I believe MSDN even introduces the term. But it's pretty simple. If you're going to write a comparator yourself, and inevitably you will, it's got to behave like operator less than. So that doesn't exactly mean you must use less than, because we've seen greater is acceptable, but operator less than is good. Operator less than equal is bad. The STL does not use comparators that behave like less than and equal. So if you provide a comparator that behaves like this, then the STL will return potentially garbage results. It could trigger debugging assertions. It could do exactly what you expect and then blow up 2 years down the road after your code is shipped to customers. Don't do it. Always behave like operator less than. And what this means is that if I have elements, say any element x, if I ask x compared to y, okay, that will return whatever I'm going to return. But what if I compare an element against itself? X compared to x. The STL requires this to always return false. An element never compares against itself because x less than x is always false. So if I started giving less than equal to the STL, well, x less than equal x is true. And the STL will then make the wrong decisions. So don't behave like less than equal. Always behave like less. The STL had to choose one or the other, and it chose less than. The other things not to do in a comparator are you can't modify elements. That would totally break the world. And you have to return answers consistently. So you can't be accessing global state and then changing your answer. So if 11 is less than 22, then it can't become greater than 22 the next time you call the comparator. The other thing about a strict weak ordering is that it has to be, it can't result in non-transitivity. So if I have x, and then I'm just going to write an @ symbol for the comparator, if this is true, and then y compared to z is true, then that implies, I won't write a symbol for that, that x compares less than z. If this is false, if x is less than y and y is less than z, but x is not less than z, then that breaks the strict weak ordering, and the STL will return garbage results, trigger assertions, or do exactly what you expect, and then blow up. So it has to behave consistently. If you really care about the details of its requirements, then go look up a strict weak ordering, but it basically just means behaves like less than. Now it's okay to consider some elements as equal, even if they're not really equal. So suppose that I had a bunch of strings, foo, bar, meow, purr, kitty, and I write a comparator that takes two strings and returns whether the left-hand side dot size is less than the right-hand side dot size. So this is comparing two strings, but instead of looking at their characters and doing a dictionary comparison as usual, it's looking only at their sizes. So this is a perfectly valid STL comparator because it behaves consistently, it doesn't return non-transitive results, it behaves like less and not less equal, but it does consider some elements to be equivalent. As far as this comparator is concerned, foo is exactly equal to bar because they have the same size, and meow is equal to purr because they're both size 4. So if I call std sort with such a comparator, it will sort them according to length. Now, what std sort says is I'm going to sort them according to this comparator that you're going to give me, but I do not guarantee that I am going to preserve the relative order of equivalent elements. So if you call std sort on a vector of string with this comparator, the foo and the bar could be in any relative order, and the meow and the purr could be any relative order, but you will be guaranteed that all of the short strings will come before all of the longer strings. If you use stable sort, this uses a potentially slower algorithm, which is why it is not the default, but it provides the extra guarantee that, yes, I'm going to sort it, but I will preserve the relative order of equivalent elements as compared to their original ordering. So if I have a sequence that says meow, bar, purr, foo, kitty, and I stable sort that, then because meow came first in the unsorted sequence, it will continue to come first in the sorted sequence, and so forth. So if you look at the most recent version 1.4 of my NeurCopy program from the previous parts, I actually do a random shuffle and then a stable sort to sort some of the elements but preserve the initial random shuffle. And a random shuffle is another STL algorithm. Look at my example for a very useful case. So that is stable sort and comparators. Let me see what we've got here. Okay, so back to algorithms. We have seen the things that you can do with binary search. There are other interesting sorts. Sometimes, and the STL has a lot of algorithms. It's a big library of algorithms, and it has somewhat more obscure algorithms that you're not going to be using all the time. But when you do need them, they can be exceedingly helpful. So partial sort allows you to sort just a subrange of a sequence. This can be useful if you only need some of a sequence sorted, but not all of it. So imagine that you've got a very, very long sequence, lots and lots of elements, maybe 100,000, and you only need the first 100 elements sorted. This could be, I'm just imagining a case here. You're displaying a page of sorted results, and you would like to display maybe the top 100 high scores or something, but you're not yet displaying the rest of the sequence, so there's no reason to sort all of it. You only need to sort the first chunk. This is exactly what a partial sort does. So regardless of the length of the sequence, you can say, okay, here's first, here's middle, and here's last, and I only want to sort between first and middle, and the rest of the elements can remain unsorted. So that's what partial sort does. And as you can imagine, trying to write this by yourself and making it efficient would be exceedingly complicated. The STL's got it for you right there. You can also ask, okay, if the sequence were sorted, what would be the nth element in that sequence in sorted order without actually going and sorting the entire range or even a subrange. So here we can see that the standard is actually somewhat readable. It says after nth element, the element in the position pointed to by nth is the element that would be in that position if the whole range were sorted. So it will essentially sort a single element into place, but not go and sort the rest of the sequence. Again, more efficient than sorting the whole sequence or even doing a partial sort. In C++OX, you can even ask, okay, is this sequence sorted? So there are other things that you can do in the STL. There are set operations. If you have sorted sequences, you can do things like, okay, I want to get the union of these sorted sequences efficiently, or I want to get the intersection, saying I only want elements that are in both sequences, or I could do a set symmetric difference. I want only elements that are in sequence A or sequence B, but not in both. And these can be done efficiently when the source sequences are sorted. You can also ask for the minimum and maximum of a sequence. This is something clever. In C++OX, there is a new algorithm called min-max. So min asks, okay, what is the least element in the sequence? Min element is the one that actually returns an iterator. And then there is min-max. Let me get that here. Min-max element. Yes. So what min-max element does is it will take a first and a last and an optional comparator and return you a pair of iterators. We've seen that before with something like equal range. And it will return iterators to the minimum and maximum element in the sequence. And here's the trick. If you were writing this naively by hand, you would have no choice but to go through every element, find the minimum, so that would be essentially n comparisons, go through every element, find the maximum, that's another n comparison, so the total would be 2n. Turns out, if you go dig through your algorithms textbook, there is a more efficient way to do this, and the STL is actually required to use that efficient way. If you look at this complexity clause, it says min-max element will perform at most maximum of 3/2 n minus 1, and then there's a floor there. But it's basically going to only perform 1.5 n instead of 2n comparisons. So min-max element is actually more efficient than anything that you would naively write by hand. There's other cases in the STL like search n, search for n, consecutive equal elements, where we can do something very efficient as compared to what you would try to write by hand. Then there are things like lexicographical comparisons, that's the dictionary ordering, and permutations. So if you want to walk through all permutations of a sequence, the STL actually has a very efficient way to do that with swapping. If you need this sort of thing, just take a look at the list of STL algorithms, and the one that you want may be there. Now, one thing that is confusing, and actually really is, about the STL is that not all algorithms are declared in the header algorithm. There are 4 and now 5 in C++OX algorithms that are actually living in another header. That header is called numeric. So most STL algorithms live in the header algorithm, but there's a few that live in the header numeric. These are called generalized numeric operations, and yeah, they do tend to manipulate numbers more often than the other STL algorithms, but if I were designing the STL myself, I would stick them all in the header algorithm instead of numeric. But that's the way it is. So if you want these other algorithms, they're hiding in clause 26, but they still can be quite useful. So they are in generalized numeric operations, and these are things like accumulate, inner product, partial sum, adjacent difference, and new in C++OX iota. So if you have a sequence of elements and you want to sum them up, then accumulate will do that for you. You give it a first iterator, a last iterator, and then an initial value for the accumulator, usually 0, and accumulate will go calculate the sum for you. It's also customizable. So if you want the product of all numbers in an STL sequence, then you can give a binary operation that will multiply each number, and of course you would want the initial number to be 1 instead of 0. So just because the default version of accumulate is using operator plus doesn't mean that you always have to use operator plus. You could be accumulating multiplication, or if you've got strings, you could be concatenating, or doing anything else that involves looking at all the elements and accumulating some result. Similarly, like with adjacent difference, you can take all of the elements and find their differences by subtracting adjacent elements. But there's other things that you can do with the algorithm by customizing the binary operation. IOTA is a new one in C++ OS. It's actually less useful than I would think. What I really want is something like counting iterator. But if you needed to generate values, it can be useful. So if you've got IOTA, first, last, and it takes a value, it will write into this sequence value, and then value plus 1, and then so forth. So if I have a vector of int v, and say I give it 10 elements, it has to have 10 elements to begin with, and then I said iota v begin, v end, and then say I want to start with 0, my vector will end up containing 0, 1, 2, 3, up to 9. So if you need data like that, then iota can be your friend. Although often what I really want is to construct the vector all at once with elements from 0 to 9. IOTA does not do that because it actually needs to write into a sequence. But that's when you can open up your copy at Boost and resort to something like counting iterator. So yeah, let's look at some other things. Transformation. Yes. So let's go back to some of the mutating sequence operations. We've seen copy, and I mentioned some of the other algorithms, but we didn't look at them in detail. Transform is a very useful one. So what transform does is it can either apply unary or binary operations. Unary just means takes one arg. Binary means takes 2 args. So if I've got transform first last result op, okay, what this conceptually is doing is it's taking a source sequence represented by first and then last, okay, and it's going to take each element, feed it through some unary operation, and then write it to result. So I could take a sequence of integers and square them all and write them into another sequence, possibly through a back inserter, or just directly into a sequence that's of the appropriate size. So transform, like the name says, applies a transformation to elements. It's also valid to do a transformation in place. So I could say transform from vBegin, vEnd, and then back to vBegin, and then give an operation. And what this will do is run each element through an operation and write it back in place. So if I want to square all the elements in a vector in place, I can use transform to do that. I could also use for each, taking an int reference, but sometimes transform is a convenient way to express it. The other way that you can call transform is with 2 sequences, and this can be very useful. We've got transform, and it's got first 1, last 1, and then first 2, result, and then binary op. Wow, 5 arguments. Confusing. Actually not confusing, because it's just talking about ranges. So we've got one sequence. This is first 1, last 1. Then we've got another sequence, and as we've seen, it's got to have at least that many elements, possibly more, because we're only going to refer to it by a single iterator first 2, but it better have this many elements. And if you look at the standard ease, that's what it's saying, although it can get kind of complicated. then it's going to be writing into some result, and it's going to be feeding elements in pairs like this to binary op, element X from the first sequence, element Y from the second sequence, and then writing them into the result. And what this can be used for is I want to take two sequences and pairwise sum them up, or I want to take strings and pairwise concatenate them, or perform any other operation. They don't have to be the same type, so I could take a string and an int and do something, or my own user-defined types. Anything that is taking two sequences and doing some sort of pairwise transformation on them, you can use transform for. The great thing about the STLs, like I've said, when you use one container, you know how to use them all. When you've used vector, you already know how to iterate through a list or a deck. There are some differences, but you know the basics. When you use an STL algorithm, like COUNTIF, now you know how to use all the other STL algorithms because they all take source ranges, sometimes destination ranges, and you can customize their behavior. And once you've used something like sort, you immediately know how to use stable sort. You just need to know about its additional guarantee. They all have very similar interfaces. So it can be a little intimidating at first because there's so many algorithms, they're taking all these things, it's phrased in this sort of mathematical language. But if you just start off using the easy ones, then you'll notice that, hey, I understand this interface of this other guy, let me try to use it. And honestly, I don't memorize the names of all these algorithms. I could probably recite most of them by hand, but what I always do is I just pop open the standard or the working paper and look for names if I want to enumerate all the algorithms. But because I've seen all of them, I'm familiar with cases where, okay, I've got to go reverse the sequence. I definitely want std reverse. Or I need to shuffle these randomly. Okay, I need to use random shuffle. When I wrote this in my Nurikabe example, I needed to look very carefully at the requirements on random shuffle's random number generator because I wanted to feed a std random Mercian twister into it, and they actually had different interfaces. What I wanted to use was the new algorithm shuffle that directly takes the Mercian twister that I had. That's not yet implemented in VC. I wrote myself a to-do about that. So I was able to take the Mercian twister that I had and adapt it with a distribution to what random shuffle required. So that's when looking at the text of the standard, it was very useful. Most of the time I just look at the signature to figure out where the first and the last and the result go. Of course, if you use IntelliSense, then that information is already being provided to you. So there you go. You have seen most of the interesting STL algorithms, and hopefully you're now ready to start using them in your code. See you next time.